This lecture is actually on ADME, so absorption, distribution, metabolism, and excretion of drugs. It's also called pharmacokinetics. It's also called just drug metabolism. All these are interchangeable terms. Various pharmacologists will write reviews and they'll argue about specific definitions of these. We don't have to get caught up in that. If you're working in this area, that might be your thing. We do not have to worry about that sort of thing. The first example I'd like to take for you to think about, and I'll swing back to this at the end of the lecture, is nicotine. So it's from a couple years ago now, this particular article, so this is just a screenshot of the article. It says free base versus protonated nicotine in electronic cigarette liquids and aerosols. So the idea is, if you look down here at the structures of nicotine, so that's the molecule nicotine, is there a difference if this is charged, if it's protonated and positively charged, versus the free base? And you should be able to think about this at a lot of different levels now by incorporating some of the stuff I told you in the first two lectures about molecular structure, about how things cross membranes. You should hopefully realize that if nicotine's protonated, it's not going to cross membranes. If it's unprotonated, it should be able to slide across very easily through membranes. It also has two nitrogens, and each of them have lone pairs. So we'll investigate that later. This article talks about manufacturers of vaping devices, electronic cigarettes, e-cigarettes. They measured the pH in all the different vape juices, and it was wildly different. And with just a slight tweak, they would be able to get more nicotine into people than they would otherwise be able to do without having to increase the levels. As soon as you start increasing the levels of nicotine, you start getting into, the regulators start making it their business to look at this stuff. So just a very simple change of just altering the pH of this solution could allow you to lower the levels of nicotine, absolute concentration, and yet get more nicotine into the person. We are not going to go into the ethics of all of this. It's a delightfully delicious area that's very controversial, more of a pub conversation. Once this lockdown ends, anybody wants to go and chat about this, we'll go down and have a beer someplace and chat about these sorts of things. So what I've told you so far is just about nicotine going across the membranes that line the lungs, then into the system, and it will distribute. But think about all these letters in this ADME: absorption, distribution, metabolism, and excretion. I'm going to walk my way through all of those using specific examples in this particular lecture. So this again is ADME. This is just a cutesy diagram I stole off the internet related to this. It's probably quite fitting. I'm going to talk about caffeine in my coffee in a little bit later in the lecture. But as I drink that, I'm getting absorption. Then it will distribute. It will go. So absorption is from the extracellular, the environment, into the body. Then it goes into the intestines or stomach. Then it circulates. That's distribution. Will move around to all the different tissues. Caffeine's actually going through my blood-brain barrier, stimulating or blocking some neurons. It's got a lot of potential mechanisms of action. We won't get into that. Again, very interesting. Go and read that on your own time. It's getting into my CNS and hopefully making me more alert, making me be able to have better word recall, these types of things. It'll also be metabolism. This is a metabolized. This is a liver, so we'll go through that. And then it's excreted. In this diagram, it's just plopping out of a person. This will be either through, most commonly, urine, but also feces, usually urine. So we'll look at how the body deals with these things and each process individually. So if we look at absorption first, how can we take a substance as external to the body and getting into us? All of this absorption in drug metabolism isn't there so that we can take modern westernized drugs in isolated forms. This is there because as we evolved as a species, or even before we were this species, during evolution, all life was hit upon by extracellular chemicals that might be deleterious. We call these xenobiotics, so foreign biotics. And the body had to have a way of dealing with these. And the easiest way of dealing with it was whatever it sees, it wants to make it so that it can't get into all the different tissues, can't cross the blood-brain barrier, and try to get rid of it from the body as quickly as possible. So it's the default route for all xenobiotics, all external chemicals, which drugs are one of them. I'll say more about how it does it later, but just to foreshadow that, basically you want to make things more polar so they don't passively cross membranes, and you want to excrete them in urine as quickly as possible. So in terms of getting things into your system, probably the most common in terms of drugs and in society, most pollutants that we would have would be through an oral route. So in drug discovery, drug development, people like swallowing tablets. It's the easiest way of going about this. There's also something sublingual. We can put certain substances just under our tongue and we will absorb them. And I'll show you a few examples of that in a minute. Buccal, again, I never used to know what the hell this is. Buccal refers to the cheek. It's like Latin for the cheek. So some things you put on your cheek rather than under your tongue. For the life of me right now, I can't remember why. There's a couple drugs that it makes sense for. I have to drink more coffee, caffeine, so that my memory improves. And then rectal. You might wonder why in God's name would anybody want a rectally administered drug? There's some very good reasons. There's some cyclic compounds that have four-membered rings, particularly certain types of penicillin. They have what's called a beta-lactam ring. If you don't know what beta-lactam is, go and look it up. It's a cyclic amide. This is a strained ring because the cyclic amide, the amides lone pair, like I was telling you, Pauling knew that peptide bonds are planar because the lone pair electrons on the nitrogen participate. They can be delocalized with other electrons. In a four-member ring, they can't be planar. So it weakens that bond. So you've got a four-member weak bond, very weak bond. The acid in the stomach would cleave that. So certain antibiotics, penicillin G usually, I think that's the one, has to be administered rectally. Also, if somebody's vomiting a lot and you want to give them an anti-nausea, antiemetic, non-vomiting drug, you can't give it orally. You could give it by injection. Rectally is sometimes preferred. Also, if somebody has epilepsy and they're in the middle of a seizure, they can't very well swallow something. It's hard to inject them sometimes. So rectally administered is more important. We'll get into blood supply and things and absorption rates, but those are the reasons for it. Parenteral. Enteral, this term means gastrointestinal tract. Per, close to, means not quite, but close to. So it's outside the gastrointestinal tract. So this will be subcutaneous, just below the skin. Intramuscular, I told you guys about anabolic steroids in the last lecture. A lot of these are really greasy. You can't take them orally. They'll stay as a greasy drop, an oily drop, but then they will slowly diffuse out of that. So that's generally an intramuscular injection. Intravenous, that's by far and away the fastest way of getting drugs into somebody. If somebody's got an acute bacterial infection and you need to get them on antibiotics, if you swallow it, it takes a while for it to dissolve, absorb, distribute. Whereas if you hit intravenous, within probably 10 seconds, it's all throughout the body. So that's by far and away the best option for getting something around the body quickly. Also for intravenous general anesthetics. So these are the ones where they find a vein, they put it into a vein. Personal pass out, the doctors get you to count backwards from 10. Most people make it to like 7 or 6. So it's very fast, less than 10 seconds throughout the body. Intrathecal, I'm struggling always, and I will quit complaining about this, that I wish you guys were here as a class because I can ask then and we can have a little short discussion about this to make sure people know what this is. Intrathecal is basically into the spinal cord, and there's like 3 layers of dura there, and they will give like a spinal block if a woman's going into labor and they want to avoid some of the pain associated with that. She'll get an epidural. This is an intrathecal injection. So that's where it comes from. They're compounds that don't distribute well. You can do a local anesthetic intrathecal injection, and it will stop wherever you are at the spinal cord. It will stop all those inputs and outputs. So it's very powerful, has to be done very precisely. Talk to some of your medical friends that might have other medical friends that have done this sort of thing. It's kind of cool. They talk about putting the needle in and then you push through one membrane, and you know, because it has this sort of feeling as it goes through. You go through too many membranes, you inject local anesthetic in the whole central nervous system, you'll probably kill a person. This happened, unfortunately, about 8-9 years ago in the NHS. There was a big lawsuit. So take-home message from this slide is there's a lot of different routes of absorption, and they all have specific reasons. So something like subcutaneous, this would be something like insulin. If somebody's got insulin, they want it subcutaneously. Because insulin, I showed you in the last lecture, insulin is a 50 amino acid peptide. So you can't just swallow this. Your body's digestive tract would just treat it like any other protein and digest it. You're not going to absorb it. It's too big. It's polar. There aren't mechanisms. There aren't carriers to take it across. So think about compounds. If you go to Wikipedia for a compound, look at its structure. Try to think about that, how that structure would impact on mechanisms, ways of taking this. So in terms of, there's this concept called bioavailability. So this is whatever means in which you administer a drug, how much is actually in your circulation, how much is in the blood. That's what this slide's referring to. So on the y-axis, we've got plasma concentration. So plasma is if you take somebody's blood, there's like 45% of it. If you centrifuge it, will be cells, 55% will be non-cells. You take that 55% that's non-cells, so you centrifuge it, you get rid of all the cells. That's plasma. Then there's also serum that I can never remember. Serum, I think, is when it's not coagulated, when you don't induce blood coagulation where the platelets all stick together, or vice versa. I can never remember that one, but it's just the liquid component, the aqueous component, salt solution of the blood. This is how we always measure blood concentrations in that. So we get rid of all the blood cells and we measure the concentration. Then there's time on this axis. These are very common plots for all this ADME or pharmacokinetics, where you look at concentration versus time. And bioavailability, by definition, this is one place where we do actually have to pay attention to what pharmacologists call bioavailability. It's the area under the curve. So that will be concentration times time. So we do the integral under these two curves, area under the curve, by whatever route that you apply it over intravenous. So intravenous is the gold standard. If you intravenously inject a drug, by definition, you're going to have 100% bioavailability. So that compares all these others. So there'll always be less than that. There's one or two really weird examples where it isn't, but for our purposes, it's always going to be less. And we get a percentage. So if we look at these curves, the IV one here, IV intravenous, starts way up here. There's no lag. As soon as you put that in, usually they inject it in one arm, measured in the other arm, 5 seconds, 10 seconds, it's from one side of the body to the other. Circulation is really, really fast. So it starts high and then it just starts dropping off. Notice the shape of this curve. There is an exponential mono, sometimes bi, usually a mono exponential curve, and we'll come to that in a little bit. If you take it then orally, here's the oral, this little triangle, you don't get very, very minimal bioavailability relative to the bioavailability of the intravenous. So this would be a drug that it's maybe too polar, too charged, it's not recognized by a carrier, maybe it's a peptide and it's degraded in the gastrointestinal tract. I can't even remember where I stole these images from. They're real data, but I don't remember what the drug is. But this drug is not orally bioavailable. So if you want somebody on this drug, you're going to have to give it intravenously. However, sometimes there's something weird going on with our nasal mucosa, the olfactory bulb and things. If you snort drugs, you can get them into the systemic circulation where we measure here, Look at this, intranasal, we get a certain area under the curve. It's probably 80% of what the intravenous is. So it's got zero oral bioavailability within statistical error, yet it's got intranasal bioavailability. So this explains why a lot of drugs of so-called abuse, recreational drugs, you chop them up and you snort them. You can get whole body distribution very, very quickly. So that's why that is there. Pharmacologically, there's a new form of a drug called ketamine, which used to be classified as a recreational drug, a drug of abuse. It's a general anesthetic. It's used in clinical practice sometimes for acute general anesthesia, like in a war zone, or when emergency responders show up, they can hit somebody with this ketamine. Has an immediate effect. It's a dissociative general anesthetic. I'll tell you much more about ketamine when I do the lecture on anesthetics, local and general. Ketamine, there's two enantiomers. I told you the last lecture about thalidomide, how drug companies now and the regulatory authorities, the FDA in the States or the EMA in Europe or MHRA now that we're through Brexit in the UK, they want drug discoverers and manufacturers to separate the two isoforms, the enantiomers of drugs. Ketamine has enantiomers. There's the S enantiomer that now it's called S-ketamine, and it's spelled ES ketamine. And this is used as a nasally inhaled drug in the States. Johnson & Johnson got approval for it, I think it was last year, maybe a year and a half ago. And this is an intranasal drug. It's used to treat treatment-resistant depression. And it works incredibly well intravenously. The data seem to show that intranasal works well. You wouldn't be able to swallow it because you don't get the high spike. You get a very low spike. So sometimes intranasal's there. The take-home message from this slide is you can calculate bioavailability by this area under the curve. It's an important concept in this because if the drug isn't being absorbed, it's going to be of no use. We have to quantify that so that we know where a drug's going and how much is getting there. And then we can do medicinal chemistry. I'll tell you more about that in the lecture on drug discovery, how we can get drugs to be more absorbed. And I'll give specific examples. In this lecture, I'll give you a few just to whet your palate on that. So some drugs can be actually absorbed through the skin. So this is an absorption route called dermal. And again, if we were in class, I said I'd stop mentioning that. Maybe I won't. I should just give up. If we were in class, we'd play this game and I'd say, why are all of these things bioavailable? They show up in the blood. If we measure plasma concentrations of these, we will see it there, even if we apply it through a patch, like up here. If you just glance through these, I'll give you guys just a minute to think about this or pause the video. Think about what's the common denominator here. Think about what are the barriers from a drug being outside the body and inside the body. Think about that first lecture I told you about membranes. It's the hydrophobic bit in the center of a membrane that dictates whether a compound's passively permeable. If it's not passively permeable, maybe there's carriers. Carriers can either facilitate gradient exchange, or they can be active and they can actually pump things against a gradient. All of these compounds are greasy. They have a certain amount of aqueous solubility, but also a certain amount of hydrophobicity, a certain amount of nonpolarness, and they will cross membranes. Some of them have very, very low water solubility. Fentanyl probably is not water soluble at all. It's given in patches. Look at the structures and correlate the structure with whether these things, whether you could guess that they would be bioavailable. Think about the log P. There's a lot of calculated log Ps. You can go on the internet, punch this molecule in, and it will give you a calculated log P. It adds up all the chemical constituents from known experiments. It's pretty damn accurate these days. So you could look at that. Are these drug-like? Are they going to be bioavailable? Fentanyl, you might know it's an opiate. So I talked about the mu opiate receptor. This is the one that's hitting opiate receptors. Fentanyl is a huge problem right now. It's killing a lot of people, between 50 and 100,000 in the States, probably 10,000 a year in Canada. Unfortunately, watch this space. It's going to hit the UK. It's starting to creep up. Fentanyl is very, very addictive, as all opiates are. And this one, because it's so hydrophobic, it's very often used as in patches in normal medicine for people with cancer or with post-operative pain. They will put fentanyl patches on and it slowly dribbles it out so that you don't get the huge spike and a decrease. So it's a very good thing. Addicts are collecting fentanyl patches, use fentanyl patches and smoking them to get their hit. These days, though, street fentanyl is very cheap. Labs throughout the world can make it. The US Postal Service, their quip is that they're the biggest drug distributors in the US right now because fentanyl is so potent, you can put it into an envelope and send it around. So that's how a lot of this fentanyl is getting there. And the amount that kills you versus the amount that gives you the high or takes the edge off your addiction or for pain control is very narrow. So it's a very dangerous drug. You stop breathing. I told you all about that. So that's the example of fentanyl. Nicotine, we'll say more about that one later, but think about it. It's got 2 nitrogens. I'll emphasize that. These other ones, testosterone, I told you about that. Any of the steroid hormones tend to be quite greasy. You give them by injection into a muscle, intramuscular injection, or through a patch. That's the other way of going about it. The one that's interesting here and kind of will make you think a little bit is this one, nitroglycerin. If you're not familiar with nitroglycerin, this is used for people with so-called angina. So they get pains in their chest because their heart's functioning and it's not getting enough oxygen to supply energy production, so that they will stop, grasp their chest, kind of be sweating profusely, have chest pains, and breathing quite deeply. So this is called angina. So if we could open up the circulatory system, the arteries and the veins around the heart, we could get more blood supply into the heart. Nitroglycerin is actually a prodrug, and it's metabolized by an enzyme I'll talk about later in this lecture called aldehyde dehydrogenase. It doesn't relate to this other than it recognizes it. It metabolizes nitroglycerin into something called nitric oxide, NO dot, so actually a free radical. This is a natural messenger molecule inside cells. They make it in a very different pathway. I don't have time to go into that. But this will relax the smooth muscle. Remember the last lecture, I showed you our vasculature can be thought of as a tube. And if you change that radius of the tube, you can have dramatic effects on blood pressure and the amount of flow. So nitroglycerin is taken, it's given through a patch or sublingually, and it gets metabolized into this prodrug, and it works within seconds. So why would nitroglycerin be able to be bioavailable through a patch or sublingually? Think about that. Again, pause the video and think about that. As soon as you hear my answer for this, you guys will stop thinking. I want you guys to think a little bit about this. Look at the structure of nitroglycerin. I said that things are membrane permeant if they're hydrophobic, meaning uncharged and not polar, and very small. It's fairly small, but it's got a lot of charge. 2 things are going on here. Overall, the molecule is neutral, but we have other molecules that are overall neutral, like amino acids that exist as zwitterions, where the nitrogen actually has a positive charge and the carboxylic acid is a negative charge. They're not soluble, not membrane permeant. They need transporters. So just overall net charge doesn't really cut it. The charge is delocalized. So I won't show you the equation, but there's a nice equation whose name is escaping me right now. There's an equation of if you have a point charge, it will attract a lot more water, a hydration shell, than if you have a spread out charge. For chemists out there, think about the properties of the halogens as you go down from fluorine down to maybe iodine. And hopefully we're recording again. Fate really seems to be against me. I'm back in a different room again. It's dark outside again. This time, well, I can't even blame Panopto. This time my webcam, my internal camera on my computer actually went down, and I reloaded the system and all that. It's not working. I'm now using a different camera. So hopefully this will work. I'm using my iPhone as a webcam that I didn't even know a person could do. We'll see how it goes. So we're going again. In case you didn't notice, there's an abbreviated cut here. My camera on my computer completely went down. Fate seems to be really against me on this. So I think where I was on this slide talking about charge. So with nitroglycerin that you see here, the charge is spread all over. So if the charge is spread all over, you don't get as much shell of water. And then I think it cut out about when I was talking about the halogens and how fluorine can get a very nice shell of hydration, very strong shell of hydration, whereas the larger halogens, iodine is probably a very good example. You get this very diffuse electron cloud, and water molecules can't go around it, so it doesn't even mix with water. Think about these things when you go through some of this. So see if I can go to the next slide. So on this next slide then, what I'd like you to look at here is this graph, and I want you to match some of these curves to the actual means of applying or administration, routes of absorption, I guess, of nicotine. So this is blood nicotine concentration. Units don't really matter. And then there's 4 different curves. And I want you to match all those curves to these different routes of administration. That's an exercise you can do on your own. And I'm not even going to tell you. You should be able to work that one out. If you have trouble with it, talk to each other, look around a little bit, think about it. These are the data that somebody got at an actual experiment, but it doesn't mean that this is necessarily always the case. There's good arguments to be made why some forms of administering a drug are faster or slower than others. So if you understand that based on the chemical principles, that's far better than just memorizing which curve goes with which. As long as there's understanding, if you maybe miss out on whether smoking is faster than nasal or vice versa, doesn't really matter. The principles, how the chemical structure impacts on absorption is the main thing with this. So on the next slide here, what I'd like you to look at and think about are 2 molecules. They're opposite ends of sort of the pH spectrum that we have to deal with pharmacology. One is aspirin, acetyl salicylic acid. So this is salicylic acid here. Here's the acetyl group. This is amphetamine. So this weird curly thing here means that we've got a stereocenter and it's just not specified. So that's a racemic amphetamine. The important thing to look at for the aspirin is this carboxylic acid group or carboxylate. And we know what the halfway point is when half the molecules are protonated and neutral in this case, meaning membrane permeant, and where half of them will be charged and not membrane permeant. So we can compare our pKa for aspirin on this carboxylic acid. It's about 3. So then if you go back to what I was showing you with those curves, those binding curves, the Hill equation, or if you must, the Langmuir equation, we can work out for 10-fold higher or 10-fold lower or 100-fold higher, 100-fold lower, what the species of ionized molecules will be, the predominant species. So in the stomach, 99% of this molecule will be the protonated form, meaning membrane permeant. So we're going to get a huge load in the epithelial cells lining the stomach of aspirin just through passive transport. Once you hit the small intestine, pH 7, only 0.01% of those molecules will be passively membrane permeant. If the molecules metabolize once it gets across, you'll still have a conveyor belt, a good concentration gradient, but there's far less permeability. So in the overall idea here is that only the neutral species will cross membranes. It's one of the theories of passive membrane transport. So for aspirin, it's the one that's protonated that's neutral. For amphetamine, we're dealing with something different. The amino group here has a lone pair of electrons, and it acts as a base. If we take the conjugate base, the pKa of that is around 10. So then we can do our calculations. You can either use the equation and get an actual number, or just sketch one and go every 10-fold away. It goes 50%, 99%, sorry, 50%, 90%, 99%, 99.9, et cetera, et cetera. And we work out there's only 1 in a million molecules in the stomach at pH 1 that would be membrane permeant. They'd all have, all but 1 in a million will be positively charged, so it won't be membrane permeant. In contrast, in the small intestine, 0.1%. 0.1% again isn't much, but if you look at the actual concentrations, you multiply the concentration that amphetamine would be at by this 0.1, and once it gets in there, it's almost an infinite sink for amphetamine. You're going to get a lot crossing, a hell of a lot more than in the stomach at least. At the very end of this lecture, I'll show you something that relates to trying to get rid of these compounds into the urine. So think about whether you would want the urine to be acidified or whether you'd want it alkalinized. Usually, very often, medical students in particular will memorize that alkalinizing the urine will be a treatment for aspirin poisoning. This is where it will acid trap aspirin or acetylsalicylic acid or salicylic acid in the urine so that then you'll just urinate it out. It's much better knowing the chemistry behind this. Then you can just look at Wikipedia, look at the structure of the compound, and know whether or not you should alkalinize or acidify the urine if somebody's overdosed on these. Amphetamines, it used to be all the rage, is a drug of abuse in sport. It was a doping drug, especially with cyclists, long distance endurance athletes. And very often they would use a certain compound to alter the pH of their urine. I'm going to let you guys think about that and figure it out. You can probably just Google it these days. It doesn't really matter. So this next slide here, there is a principle here in which if you've got compounds that aren't passively membrane permeant, all is not lost. There's so-called prodrug strategies where you add a group onto the compound and it mimics the endogenous substance, and then you hijack a carrier and a carrier will take it across. The best example, sort of the first example of this, was something called valcyclovir. So if we just take a second and look at the compound here, this in dark and black is acyclovir. It's acyclic. This group here with 1, 2, 3 carbons and an oxygen, that is acyclic ribose. So look at ribose. Ribose normally has 2 hydroxyls on it. So this is a base, and then we have ribose on it. So it's a nucleoside. It's a nucleoside mimetic. It gets into cells that have been infected with viruses, and it gets phosphorylated, and then the viral DNA polymerase can't use this as a substrate. It terminates it because there's no 3' hydroxyl on it. So look at a ribose, notice the 2' hydroxyl, the 3' hydroxyl. If we were doing this live, I'd use a whiteboard and draw this out. But just notice that you go from a cyclic ribose to a non-cyclic ribose or acyclic. So acyclovir was a very good drug. It was discovered by this lady here, Gertrude Elion, got a Nobel Prize for some of this work, anti-cancer agents, nucleotides for anti-cancer agents, and antiviral agents. They work on very similar principles, actually. So Gertrude came up with this. I'd encourage you, I'll try to remember to put it up on the web, a couple biographies of Gertrude Elion, an amazing, absolutely amazing lady, back when there weren't a lot of females doing this type of research and weren't getting the due credit for this. So acyclovir works really well, not orally bioavailable. So what they did then is they attached the amino acid valine. That's what's over here, the amino acid valine. Valine goes through a pump, a transporter. all the amino acids that we uptake in our diet have to get a ride on a transporter because they have two charges. There's Zwitter ions. So here, adding valine to this allowed it to catch a lift on that transporter. And what happened, instead of acyclovir having an oral bioavailability, so that's if you swallow 100 milligrams, you'd only get 10 milligrams showing up in the blood. That's by definition oral bioavailability. Whereas if you put this valine on it and get valcyclovir, you get 60% coming through into the blood. A lot of people have used this strategy. It's nowhere nearly used as much as it should be. For some reason, a lot of people, when they hit non-bioavailable drugs, they don't think of this, whereas I think it's a fantastic strategy and would love to see more of that. So now we've talked about uptake, passive uptake, carrier-mediated uptake. We've thought about polarity, we've thought about charge, we've thought about ionizable groups, we've thought about the effects of pH on aspirin and amphetamine. Now I'd like you to think about distribution. So this is once it's in the circulation, where does it go? It's subject to, as I wrote down here, the same underlying concepts. The unison concept is membranes are barriers. That hydrophobic core of a membrane, is the barrier that allows or stops small molecules from spreading across a membrane. So we can think back to that first lecture I gave you, and I said, how fast do things go across the membrane? There's the pressure, the concentration gradient over the resistance. The membrane's the resistance. We can overcome that resistance by having things that dissolve into the membrane, that partition into the membrane. So it's log P, partition coefficient. It's also the concentration. So if we understand those two things, everything that you read in the textbooks about what controls distribution of these small molecules will make sense. It boils down to those concepts. So if we look on screen here and it says it depends on ionization, partition coefficient, that all makes sense. Capillary permeability. I showed you the blood-brain barrier where two cells come together. There's tight junctions. Any molecule that gets across the blood-brain barrier has to go through two plasma membranes of a given cell. One at the blood endothelial cell barrier, then the endothelial cell brain barrier. So it has to go through that either passively or through a carrier. So other capillaries in the body, so capillaries are the really small blood vessels that go through veins and arteries, and they go through down to just a couple cells. Red blood cells can almost block them. They get that small. And some of them have cells that are a little separated. They're leaky. Other ones, like the blood-brain barrier, they're very tight. So it depends a little bit on that. Also blood flow. So if you are perfusing a tissue a lot, so the brain's the most perfused tissue of anything. After that, I think it's the liver, then it's skeletal muscles. So there's a hierarchy of tissues that get perfused with a lot of blood or not much blood. Fat is probably the lowest. So greasy compounds will partition into fat, they'll distribute into fat because it's not, the circulation isn't that fast there, it's not perfused that much. They will sit there a long time. When I give a lecture on general anesthetics that are kind of greasy, they'll stick around for a long time. You can get general anesthetics hangovers because of this lack of perfusion in very greasy compounds that are used as general anesthetics. Plasma binding, the last point down here, that should make sense. There's proteins in your blood. Albumin is probably one of the biggest ones, and they have little patches that can bind molecules. Albumin, I think, has 7, 8 little pockets, surface depressions that bind greasy compounds. Endogenously, this would be steroid hormones, free fatty acids. If we give drugs that are slightly greasy, albumin is going to bind a lot of that. It's going to drop the free concentration of the drug. So with all of these things, the concentration of the drug we're interested in is not the total, meaning that which is bound and free. We're interested in the free. The reason we're interested in the free is that's the form of the compound that enters into these mass action diagrams, the mass action equations. It's the one that gives us a thermodynamic driving push. So it's a free compound. So if something binds to a lot of plasma, it's not going to be there to cross membranes. Looking at this graph now, it should all make sense. So what we're looking at is the the concentration of the drug in each of these different compartments. They're over to the right here. And you can see the plasma shoots up. Then once it's in the plasma, it starts to slowly go into the other systems, and then it'll hit some equilibria. All these are rapidly changing equilibria, but you'll get sort of pseudo steady state with things. And you can see the brain gets perfused a lot, so that's the next one. And if you look at fatty tissue, you don't see a lot. So this compound, I can't even remember what compound this one is. It's probably not very hydrophobic. It doesn't go into fatty tissue. You can imagine if you have compounds that are really polar, they're not going to distribute very well. If you have compounds that are really hydrophobic, they're going to go everywhere. As examples of that now, let's look at this one. So some very specific examples of distribution. Ethanol. So ethanol is 2 carbons, 1 hydroxyl, 1 methyl group, CH3. So it's kind of intermediate. It's got a little bit of polarity, a little bit of non-polarity. It's hydrophobic, hydrophilic. It'll go everywhere except into fats. It won't go into fats because of that hydroxyl group. So it partitions everywhere where there's water in the body. I'll say more about ethanol later in the lecture. Heparin. Heparin's a really big molecule. You give it as an anti-clotting agent. It prevents some of the intermediates in the clotting cascade where platelets stick together. And if somebody is getting thrombosis or is at risk of getting thrombosis, you give them heparin. My mom had deep vein thrombosis, and she was given injections that she had to give at home that were subcutaneous of heparin. Heparin is a very large polymer of glucose-like units, but they have sulfates and carboxylates on it. So it's very big and highly charged. This was back before I knew all this stuff about pharmacokinetics, and I was wondering how the hell does this stuff go into the rest of the body if she's just injecting this heparin subcutaneously? It's because the capillaries are leaky in a lot of these tissues, so it wouldn't cross the blood-brain barrier. It leaks out into these other tissues, and it will go to the site of action in her legs and prevent deep vein thrombosis. So non-drowsy antihistamines, I'll say a little more about that when we hit the drug discovery lecture. In a nutshell, some of the histamines are very drowsy inducing, like diphenhydramine. Histamine receptors are those belong to the group of G protein coupled receptors. There's 4 types. H3, histamine receptor type 3, is in the central nervous system. If you antagonize that one, you'll get very drowsy. This is why certain antihistamines cause people to get drowsy. What they're trying to inhibit is the H1 antihistamine receptor with these antihistamines. That's the one, if you get hay fever, it will block that one. And some of those mast-like cells release histamine, and they will cause swelling in your nasal passages, mucus production, runny eyes, runny nose, all of those sorts of things. So if you make the antihistamine bigger and more polar, it doesn't cross membranes passively, and you can prevent it from going into the central nervous system. So that's one way of going about this. I'll skip sodium pentothal, truth serum. It's a cool story, but I already take too long with these lectures. You guys can look it up. It was big during the Cold War. Kind of missed the Cold War, all the spying, East versus West stuff, and they used a lot of pharmaceutical agents. If you're interested in that sort of thing, the Americans had a program called MK Ultra, where they used a lot of compounds, LSD, mind control compounds, what they thought, truth serums, all these things. It was all covered up. Then it was a big scandal. Things got released. People had experiments done on them that they were not consenting to. All of it didn't work, basically. They were also looking at astral projection. They called it a so-called psi gap with the Soviets. They thought that they would be able to, look at submarines just by the power of the mind across the world. Really cool stuff if you're into that. Dioxin, this one I'll say a few words about. So dioxins, as the name suggests, di, 2, oxen, oxygen. So if you have 2 oxygens and they're across from each other, it's a 1,4 dioxin in a 6-member ring. So you've got a 6-member ring with 2 oxygens on it. Then you can add 2 benzenes on either side of that ring. Now we've got a 3-ring structure. And then now we've got dibenzodioxin. And then we put chlorines at, can't even remember which groups. It's like these corners and these corners. I could draw it out. This particular compound is a dioxin. And these dioxins are carcinogenic, they're teratogenic, they are very hydrophobic because they've got chlorides on them, chlorine on them. They are aromatic, they partition into fat. So if you get even low levels of this over a long period of time, you'll poison yourself because your fat stores will just keep accumulating this. They're so greasy that you'll never get rid of them. I'll come along to in a little bit in this lecture where I talk about oxidizing some of these sites on benzene. So the idea of metabolism is you oxidize it, make it more polar. If you put chloro groups on this, you can't oxidize it. Our enzymatic machinery can't. So these dioxins just keep building up and our body can't make them more polar, so we can't urinate them out. So it's a big problem. They got around this with some dioxin poisonings by adding something called olestra. Look up the structure on Wikipedia. Basically, it's sucrose, so that's a fructose ring and a glucose ring fused together. It's an alpha linkage, if memory serves, between the two. And then at every hydroxyl, or almost every hydroxyl, they added stearic acid. Remember stearic acid from the first lecture? 18 carbons, fatty acid, and they esterify this. So you've got this little 2-sugar unit with all these long fatty acids esterified to it. The body's enzymes can't get to that. So these things just sit there as globules of fat. We can't digest them. They just go right through the gastrointestinal tract. It was originally designed by General Mills, I believe, in the States as a non-caloric fat that they would put into food. Unfortunately, it had a few side effects. They weren't as severe as the media made them out to be, but it had things as charming as anal leakage, this sort of thing that was caused by some of these fats. So Frito-Lay, that company as well, you'd eat taco chips, crisps, and you wouldn't absorb the fats, but it caused gastrointestinal disturbances. It got such bad press, it wasn't available out there. More recently, people have used olestra as a treatment for dioxin poisoning. They fed people a lot of this olestra. And if you get fats up close, globules of fat of olestra, up close against some of the gastrointestinal tract, some of the dioxin will partition into that and it'll go through your system. They were able to drop levels of dioxin very quickly like this. Some of you, I'll forget his name, but it's like Viktor Yushchenko, a former prime minister of Yugoslavia, was poisoned intentionally with dioxin. You get something called chloroacne from this. I used to think it was from halogens, but it's mostly polyaromatic hydrocarbons. It's particularly bad if they have halogen groups on it, very often chlorine, because then you can't metabolize it. Look on the internet. He got really bad chloroacne. He didn't die, but it's devastating. And then they used olestra to treat him with this, and he allowed his name to be used in that. So there's a couple case studies out there regarding this. So just think about the implications of this. Somebody was thinking very broadly. You can just read about this stuff in a textbook, and they're never going to show you this. Whereas if you think about some of this stuff, you might be the GP or the advisor to a GP who is able to use some of these other techniques to cure somebody of dioxin poisoning. The last one, ethanol concentration in the breath. This is how breathalyzers work, police check stops where you blow into something. We know that for every 1 unit of alcohol in the breath, there's 2,100 in us on average. That varies between people between about 3,700 down to probably about 1,900. So that's why, at least in Canada, if you fail a roadside breathalyzer test, they take you in and do a blood level. So you'd actually do plasma alcohol concentrations. I'll say a little more about alcohol metabolism later in the lecture. There's some cool stuff that surprised me. I thought they were wrong. I read about it in a tabloid. Turns out it's real for getting rid of ethanol faster than just enzymatically. So another aspect of metabolism that I think is very important. So I'm trying to just give you specific examples on certain things. I leave it up to you then to use those examples more broadly. There's something called first pass metabolism. So when we swallow something orally, this only happens for oral drugs. Here's a little cartoon. So the oral medication goes into the gastrointestinal tract. Most of the uptake will be through the small intestine. It then immediately goes through a vein, the portal vein, to the liver. So the liver is like the molecular paper shredder of all these compounds that we ingest, all the xenobiotics evolutionarily nowadays if we're taking drugs. And some compounds get shredded by that molecular paper shredder. And this is one really cool example. The net effect of that is oral bioavailability decreases dramatically. So here's a compound called estradiol. I showed you in the first lecture progesterone. This is related to progesterone. It's one of the female sex hormones. And people tried it initially as an oral birth control molecule tablet, the first pill. It failed because it got metabolized up at this site here. This is the C17 site. There's a lot of numbers on here. That's one of the ones that it's kind of, you don't have to know it for the course, but it's useful to know a couple of them just in terms of life. If you're interested in looking at molecules, the C17 one's an important one. Normally that would get metabolized by something called Cytochrome P450. I'll come on to that in a minute. And it would go from a hydroxyl group here to a ketone, would lose all activity. So in first pass metabolism, before it even hit systemic circulation, the liver chewed this up, it oxidized it, and it wouldn't work. So what people did, this is really clever and really straightforward and really simple, and a lot of drug discoverers are doing all sorts of high throughput robotics, big data stuff, whereas if they just used their brains and thought a little bit, nobody's applying this sort of thing anymore. I think it's a real shame. What they did out here is added this carbon triple bonded carbon. I would say it's an acetylene group and an an acetylene group. You guys would call it like an ethyne group, I believe. Anyways, it's carbon, 3 double bonds. On these steroid rings, we very often call something alpha or beta. Alpha means it's behind the plane of the ring when we draw it this way. Beta means it's towards us. So they added this ethyne group in the beta position. What that does is it sterically hinders oxidation at this C17 position. So the enzyme can't get its little enzymatic jaws on it to oxidize it properly. This was a first oral birth control tablet because you could take it orally. Estradiol would work, but you'd have to inject yourself every day with it. There's usually a reluctance for people injecting themselves with things. There's a lot of needle phobias out there. People just don't like it. Sometimes it's necessary, as with insulin. But otherwise, you always want an oral form. And I think I said in the first lecture, oral birth control revolutionized women's rights. It's arguably the starting point from a lot of this, so pharmacological basis of that. It also led to the sexual revolution of the 60s. Did a lot, all from this one molecule. So in terms of metabolism, if you forget everything else in this lecture, think about it in two things. There's phase 1 and phase 2. Phase 1, you add a functional group or reveal a functional group or put a handle on it, as I often say. Phase 2, you conjugate that. You make a covalent bond to some endogenous metabolite that's very, very polar, very hydrophilic, very water-loving. And what this does is it gets filtered through the kidneys into the urine and you pee it out. So something like dioxin, the body can't do this, so it accumulates in fat. Whereas other compounds, they will get metabolized, they get oxidized and tagged and peed out. So phase 1, very often, probably 90% of it is oxidation, but can be these other things. It can be reduction, hydrolysis, ND-alkylation. I'll show you caffeine in a few minutes that undergoes that one. And then they connect it with something like glucuronate. So glucuronic acid is glucose, but the C6 position is oxidized to a carboxylate. So this pKa will be around 4-ish. So most of it will be a charged, negatively charged at physiological pH. So if that goes into your urine, unless you have pumps to take it back up, it stays in your urine and you urinate it out. There's also sulfate, glycine, glutathione. All of these are small and very, very water soluble. Usually it makes the compound less toxic. There is some cases where the oxidation of the drug will make it more toxic, and I'll walk through probably the most infamous example of that, and it's very common and very interesting, is paracetamol. Go through that in a second. Also, some drugs like that, nitroglycerin that I showed you a few slides ago, that will get metabolized by aldehyde dehydrogenase into nitric acid, nitric oxide, NO dot, and that will relax smooth muscle. So that's a nitroglycerin, glycerol trinitrate. You guys might be more familiar with that nomenclature. It gets metabolized, so it's a prodrug. In terms of metabolism, this cytochrome P450, I wish I had time to go through a whole lecture on this. It's a really, really cool enzyme. If you're into that sort of thing, you don't have to know it if you're not into it. Don't worry about it that much. But if you're into this, it's really cool. Chemists are usually, pure chemists, are surprised by this. Cytochrome P450 can oxidize hydrocarbons. So like just straight chain hydrocarbons or even benzene can introduce oxygen. It can tear off hydrogen plus 2 electrons of hydride and put oxygen on there through a free radical mechanism. But it can do this at physiological pH, room temperature, and body temperature, and in an aqueous environment. So this is an incredible enzyme. It can oxidize just about anything other than some of those chlorinated or halogenated compounds. So if you see any of these halogens on compounds, usually they don't occur in nature other than iodine, which I showed you for thyroxine, this hormone from the thyroid gland. Most of the time when you see that, some medicinal chemist has introduced that to try to alter metabolism. Just very, very briefly on this, it's called cytochrome P450 because in this form, when carbon monoxide is bound to the cytochrome, this is a heme group, meaning it's a tetrapyrrole ring. So it's got 4 5-member rings with nitrogen. All the nitrogens have lone pair electrons pointing into the center, and the center you have iron. This is just like the heme group in myoglobin or hemoglobin. On the other side, can't remember on this one, I don't know if you have a histidine as one of the other coordinating centers, the Lewis base. And then on the upper side, oxygen can come and bind, or carbon monoxide. When carbon monoxide's bound, its absorbance is 490 nanometers. So that's why it's called cytochrome P450. That's its absorbance peak in its absorbance spectrum. And like I say, it undergoes a free radical reaction cycle. I don't have time, sadly, go into more detail on that. But if you're into that, look it up. Some of the effects of cytochrome P450, remember I said drug metabolism usually detoxifies drugs, but sometimes it can make them more toxic. And that's what the slide's about, using paracetamol as an example. So if we look at paracetamol initially here, in the center upper of this, it's look at all the conjugation here, alternating double single, double single. These electrons just flow all over the place. It's just a lot of electrons delocalized. Normally, so again, let's look at this. Metabolism is supposed to make or reveal a group that you can attach, you can conjugate some soluble product. Here we already have a group that we can attach a soluble product. So we've already got a hydroxyl group here. So we don't necessarily have to go through that phase 1 oxidation step. We can just jump straight to phase 2 and conjugate this. So 60% of it is conjugated with glucuronate, urinated out. So it goes into the blood, gets filtered in by the kidneys into the urine, and then it's urinated out. Or sulfates. So sulfate's another one. There are UDP glucuronate transporters, enzymes that UDP glucuronate not transporters, transferase. My mind is going. So transferases that transfer this. You need a little bit of energy with these diphosphates, and similarly for sulfate. 90% of it goes that way. If you take normal sort of therapeutic levels of paracetamol, maybe half a gram to a gram at a time, no more than 4 times a day, so a daily limit of about 4 grams. 10% of this, though, will be acted on by something called a cytochrome P450 2E1. This is sort of the genetic nomenclature for this. So we have protein nomenclature and gene nomenclature. And cytochrome P450s, just like receptors or any drug targets, come in families. So we number the families, 1, 2, 3, 4, 5, 6, etc. And then there's subgroups within the families, and we start labeling them with numbers, letters. And then there's subgroups within the subfamilies, and then we start using numbers again. So it can get really hairy. For this, all I want you to know is that there's a subtype. There are subtypes. And one particular subtype, the CYP, people that are working in this area pronounce that acronym. So it's a CYP2E1. These are for small molecules. I'll show you in a minute a pie diagram that shows most of it is a CYP3,4A, which deals with really large greasy molecules. This particular CYP will oxidize the molecule. I've omitted a few steps here. We don't have to do the full electron pushing, but you might want to try that yourself. It's character building and it's kind of fun. Here what happens is the nitrogen gets oxidized. This then leaves and we get electrons. These snap in, these snap up, these snap up. We're left with this compound down here, which is called N-acetyl. So there's the N-acetyl group. P for para-benzoquinonamine. This quinonamine is the thing that we've got to worry about. This structure here is a very hot electrophile. It's a Michael acceptor. Michael acceptors are when you have a double bond here and a keto in the alpha position away from it, beta. In a cell, a lot of proteins have cysteines. This has a sulfhydryl group as a side chain, SH. So this SH is a good nucleophile. It will attack the electrophile here and we get electrons moving. Now we've conjugated our compound to a protein that has a sulfhydryl, or here to glutathione. Glutathione is a tripeptide gamma-glutamyl-cysteine glycine, and that sulfhydryl group on the cysteine can undergo this reaction. And this is what will happen if you take normal amounts of paracetamol. You'll make 10% of it into this toxic product. Glutathione will mop that up. We have between 1 and 10 millimolar glutathione inside most cells, so this isn't a problem. If you take a lot, if you take over 8 grams of paracetamol, you'll start to maybe have problems. You'll start eating up all your glutathione. Once all your glutathione's gone, you'll get into difficulties. Not only that, you'll saturate these two conjugation enzymes. So these two phase 2 enzymes will get saturated. They have binding sites. There's a KM. There's only so much that they can take. And it starts shunting all this paracetamol through this CYP2E1. So you'll get a real onslaught of the toxic metabolite. You'll eat up all your glutathione. Then you start reacting this quinonamine with protein that has sulfhydryls. You'll cross-link it. Protein function will fail. Your liver will fail. And your cells will die. Your liver will die. If you take probably 16 grams of paracetamol, you'll destroy your liver. If you're not treated within 24 to 48 hours, your liver's destroyed. The only chance you have for survival at that point is through a liver transplant. So this happens a lot. Happily, a lot of people end up in A&E and they can correct this. This is a popular way, if I can use that term in this horrible context, for people to try to commit suicide, but it does give them a time frame, and very often they change their minds, go to A&E, and they give them a compound down here in the lower right called N-acetylcysteine. So the N-acetyl group helps with the bioavailability of this compound. It makes it a little greasier. increases passive membrane transport. And the cysteine is a component that's used to make glutathione, so you can build up glutathione levels. If you catch it within 24 hours of paracetamol poisoning, everything's fine with N-acetyl cysteine. If you're beyond that, 48 to 72 hours, liver transplant's all that you really have at that point. So you might wonder why I've got a dead cat down in the lower left. This is not to mean that cats have a problem with taking paracetamol, but if they did, there is a problem. If you've got a cat, don't give kitty paracetamol for her arthritis. Cats do not have these conjugating enzymes. So any paracetamol given to felines will be metabolized exclusively through this toxic metabolite. So paracetamol is incredibly toxic to cats. In terms of some of the other things I was telling you about here, readjust here for a second. So with this particular slide, we're looking at another phase 1 metabolism, but here we're not looking at oxidation per se. We're looking at oxidation, but we're not incorporating oxygen. What we're doing is doing N-demethylation. Excuse me. This is for caffeine. Caffeine's trimethylxanthine, it's shown down here. Interestingly, a lot of these compounds that caffeine gets metabolized to have pharmacological actions. Some people say they can't have tea because of the caffeine in it. Tea has a lot of, let's see, where is it? Theophylline and theobromine. Some of these are vasodilators, so people will get flushed from tea, whereas not coffee. Every one of us is going to have slightly different, look at all these Cytochrome P450s. We'll all be individuals with this. We're all going to have a certain signature of Cytochrome P450s. Some of them will be fast metabolizers. Some of them will be slow metabolizers. Some of them will have different metabolic pathways. So some people can drink coffee just before they go to bed, say no big deal, they're just used to it. They might be fast metabolizers of caffeine. We now know enough about it. You can do genetic tests. You can send your DNA sample off to that California company, 23andMe, and this is one of the things you can look at when you get your results back. Are you a fast, medium, or slow metabolizer of caffeine? Put it up here just because a lot of drugs have an N-methyl group on it, and then the metabolite is nor whatever the compound is. So ketamine, I mentioned earlier, one of the metabolites is norketamine. There's arguments in the literature as to whether that's the active compound or not. So you'll see this as a step in the metabolism of a lot of drugs. Caffeine's just there for you to look at as an example of this. So one very curious thing that's out there is a so-called cheese syndrome. So that's written up here on the right. This involves something called monoamine oxidase inhibitors. So monoamine oxidase, that's Cytochrome P450, it's got different families. Any molecule you throw at it, it's going to be able to oxidize, other than the ones with chloro, bromo, iodo, fluoro, the halogens. It'll be able to oxidize them, no problem. And then you get conjugation in that second step and urinate it out. There are some metabolic enzymes that are more specific. These are for neurotransmitters. So they're monoamine neurotransmitters because they have a single amine. The side chain can be here like catechol for noradrenaline, adrenaline, dopamine, or it can be this indole group here, 5-hydroxytryptamine, 5-hydroxyindole is a side chain on this one. They're all monoamines. The amine group can get oxidized, and it will be oxidized to an aldehyde, and with the release of ammonia. So that's the normal metabolic route with this. So some of the neurotransmitters taken up on those carriers, we talked about that. Some neurotransmitter does get metabolized through these. The very first antidepressants that fit with the monoamine theory of depression, which Trevor Sharp will tell you more about in his lecture on neuropsychopharmacology, of CNS issues, of mood disorders. He'll tell you more about the monoamine theory there. The idea, well, just very briefly, you won't know where this is going. Think of monoamines like 5-HT. If you've got the proper level, you're balanced. If you've got not enough, you're depressed. So how do we get that up? I showed you those SSRIs, the serotonin selective reuptake inhibitors, so we can keep more in that synaptic cleft. Another way of doing this is you inhibit its degradation. There's just more of it floating around then. That's the idea behind this. And it was an accidental discovery. A lot of this science was accidents. But as Louis Pasteur said, accidents favor the prepared mind. So somebody had to realize the importance of this. And I'll give you a little background on this because it still illustrates how drug discovery used to be done. Everybody thinks we've got great control now. We know everything and we can do everything. Drug discovery is failing for the most part, unfortunately. At least not nearly as efficient as it used to be. So what was happening is there was a compound called isoniazid. It's related to this iproniazid. It was a tuberculosis drug. And this was back in the 1950s, probably. Tuberculosis was pretty much a death sentence. You slowly died, unlike COVID, where the death comes a little faster. A lot of people had tuberculosis and they would die over a period of years, and they wrote great literature during this, and it was a very emotive time. They had whole hospitals devoted to people who had tuberculosis. They tried to give them nice, clean, dry air, trying to sort of slow the inevitable demise. So these were quite dreary places, and as one could imagine, everybody there pretty much had a death sentence. And they started giving this antibacterial compound, iproniazid. And weirdly, the nurses observed the patients, and the patients got quite jolly. They were hitting on all the nurses. Back in the day, most nurses were female. So there's all these stories. You read the original paper on this, and it goes into detail about some of this. And some of the doctors looking at this said, it's improving mood of people that should be very, very depressed. Maybe it would improve mood of, in quotes, depressed people, normal depressed people. So they tried it and it worked. So this was the monoamine, fit with the monoamine theory of depression. We had monoamine oxidase inhibitors that covalently linked to the enzyme. So this is one of those unusual drugs that covalently links to the enzyme. So if you do the mass action, that arrow is just one way. In terms of more modern ones, iproniazid, we now have inhibitors that aren't permanently covalently modifying the enzyme so that you can wash on drug, you can wash off drug. This cheese syndrome comes from this effect. So what happens if we eat fermented foods? Very often fermented foods have a lot of an amino acid called tyrosine. The bacteria or fungus that does the fermenting converts tyrosine to tyramine. Tyramine is recognized, it's taken up by a lot of these transporters, and it will act on noradrenaline receptors. That will increase blood pressure dramatically to the extent that people will have hypertension, headache, they will get a stroke, a cerebral hemorrhage, because your blood pressure will go up that much. Normally, if your monoamine oxidase is working fine, tyramine's just taken care of in the wall of the gut. We have monoamine oxidase there, first pass metabolism. You will not get tyramine in your blood supply. It has zero oral bioavailability. But if you're depressed and you're on monoamine oxidase inhibitors, particularly these covalent ones, you absorb the tyramine, and you end up getting these effects. This has killed probably around 100 people, if you believe the case reports on this. So it's rare, but it still can happen. It's an interesting story in terms of what we know about the pharmacokinetics and drug metabolism in it. In terms of fermented foods, it's things like cheese, Chianti wine, Marmite, anything where there's been yeast or bacteria tends to do these. So if you ever are on monoamine oxidase inhibitors, or if you look at the guidelines on them, if you guys are medics and you have patients, it will say, do not take this with cheese, Chianti, Marmite, etc. The list might not be extensive. Just make sure you don't take it with any of these fermented foods, which is very broad and gives us a conceptual understanding of this. So moving on now to, where we are. We've gone through a few examples: absorption, how do things get into us, passively or through carriers, all the factors that affect that. It's mostly whether they cross membranes passively or through a carrier. Then we looked at distribution. We were then looking at metabolism, phase 1, phase 2 metabolism. Now we're looking at more specific ones. So we just looked at monoamine oxidase as an enzyme and the effects of inhibiting that. Now we're going to look at alcohol metabolism, alcohol dehydrogenase, and aldehyde dehydrogenase. This is, I think, again, quite interesting. So in this slide, what we're looking at is breath alcohol. So this is breath alcohol. I converted it to blood alcohol at one point, and I can't remember where those notes are, and I've forgotten to go back and do that. But basically, blood alcohol, these are drinks up here. So 3 drinks, then a break, and then another drink. So they are giving people drinks on an empty stomach in a controlled lab setting. Time along the bottom axis is hours. And you can see they're giving 3 drinks. It's just going up. And then it kind of plateaus. They give another drink, it jumps up. Not that interested in the first bit of this particular plasma concentration. We can think of it as plasma, it's breath alcohol. But remember, for every 2,100 units of alcohol or moles or molecules of alcohol in us, one of them will be in the breath. So it should be easy to convert it back into plasma levels. What I'd like you to look at here is that after they stop drinking, this is the last drink, it's linear. Remember that earlier one? I showed you a couple of these. They all showed exponentials. If it's a linear plot, they show exponentials. If it's linear with this, it means it's zero order kinetics. We can understand that really well for alcohol. What happens is, here's the Michaelis-Menten plot. This is enzyme velocity. This is against substrate concentration, linear. We get a rectangular hyperbola. That looks a lot like a binding curve. Other than that K-cat, usually we can ignore the K-cat, say that it's way slower than K off the back reaction. And we can fit this with Michaelis-Menten or Hill equation. They're about the same thing here. Notice that all biology saturates. Remember, I told you guys in that one lecture, chemistry just keeps going linearly up. If you start seeing a plateau, we've got saturation, that's biology. The plateau here is due to number of binding sites on alcohol dehydrogenase. The interesting thing is it saturates around 1 millimolar. Over here, this would be just very, very roughly, this will probably be about about 8 millimolar. 8 millimolar is when you probably, I'd have to double check, but so check on this, don't take my word for it. 8 millimolar is about where you're legally impaired driving. So you're 8-fold above the km here. So after a few drinks, you're way over here. You can't make that enzyme go past its Vmax. All the binding sites are saturated. So you get this zero order kinetics rather than first order kinetics. First order kinetics is when velocity depends on substrate concentration. So anywhere along here where this is linear, once it saturates, you're at zero order. So that's something that's really curious for alcohol. One of the things that you can use this for, wouldn't necessarily recommend it, but growing up in Canada, there were pubs that were in the middle of nowhere. It was a horrible culture in that people weren't as concerned about drink driving. And people would drink, and you knew that you metabolized about 7 grams an hour, 1 drink an hour. So you'd have 3 beer, wait 3 hours. And if your liver is working properly and you fit into the normal distribution, you could drive again at that point. It's gotten more enlightened there now, but that's the way people used to do it. So you guys, if you're out drinking and you know how many drinks you had and you have to get up in the morning to go and row or go and write an exam or something, you can do a rule of thumb calculation, 1 drink an hour, basically. And everybody's very close to that. So I'll show you in the next slide or two where I first heard of this. And then this I took from the actual journal article that just a couple months ago in Scientific Reports. So this is a journal. This is where you can look it up if you want to see the whole journal article. And it's accelerated ethanol elimination via the lungs. And the tabloid stories on this one were that you can sober up faster by hyperventilating, basically. And I was thinking about this and I thought complete bullshit, because you think about it, there's 2,100 units in you. There's only one in your breath. So you'd have to take, to get rid of 1 unit in yourself, you'd have to breathe 2,100 units in to drop that. So it just didn't seem realistic. I went and read about this and it actually works. So sometimes common sense, first principles doesn't get you there. You look at the data, as Feynman says, if your hypothesis doesn't fit the data, your hypothesis is wrong. My knee-jerk reaction with this was wrong. What we're looking at here is blood alcohol concentration as a percentage. And what they did was, what we're looking at here, let's look at the blue. So they gave the people in the blue no IH. That was Isocapric Hyperventilation, I think it was. It means they keep the CO2 level high in you so that you keep hyperventilating without going dizzy and passing out and all these things. So it's a way of keeping carbon dioxide levels very high so that you can hyperventilate, not blow off all your CO2 and change the pH of your system. In the control group, look at this, linear kinetics. So there's some bounce in the data, but they did a linear fit on this. So they gave them drinks up to this point, and then they just watched how blood alcohol, breath alcohol dropped. It dropped linearly within the error here, the control. What's amazing to me is this is with hyperventilation. Here's where they started hyperventilation. And the curve goes from linear, 0 order, to exponential, which is 1st order. And they were able to show this. It's absolutely phenomenal. So maybe for alcohol poisoning, this is a way where people could get rid of alcohol quite readily. The ideas behind this very often, or did actually, come from some of the volatile general anesthetics that I will tell you guys about in a couple weeks. I guess that lecture is coming up. So I was shocked by this. You guys probably won't be as shocked because you don't have all this preconceived notion regarding this. So in terms of actual alcohol metabolism, I'm just writing ethanol out here. 90% of it's metabolized by alcohol dehydrogenase. Guess where the 10% would be? Again, if we had a class, I would ask for guesses. Since we don't, that 10% is by one of the cytochrome P450s, the CYP2E1, the same one that does paracetamol oxidation to that toxic metabolite. If people drink a lot, they will get upregulation of that cytochrome P450. It's not enough to cause problems. I have a whole slide on that in a second if you're drinking alcohol, but everybody worries about it. Anyway, alcohol dehydrogenase, we get an aldehyde. The aldehyde then has an aldehyde dehydrogenase, and it takes it to the next state of oxidation, which is the acid group. So we get acetic acid. That then just enters into metabolism. Alcohol dehydrogenase is almost exclusively present in the liver. There's a little bit in the central nervous system for reasons we don't understand. It's mostly in the liver. So your liver metabolizes this. And then you metabolize acetic acid and you get a lot of reducing equivalents, NADH. It'll convince your body that you don't need to eat. You'll put fat down in your liver. This is the origin of alcoholic fatty liver disease. You get so many reducing equivalents, the liver decides to just store fat. And this will cause problems in chronic drinkers, liver cirrhosis. You get fibers accumulating in the liver, all these problems. It's due to this metabolic pathway. Aldehydes are incredibly reactive. If we look at this one, formaldehyde here, just single carbon, simplest aldehyde we have. Medics will know this one because a lot of the cadavers are so-called pickled or denatured with formaldehyde. You can run through the electron pushing chemistry on your own, but any amino groups off amino acids or off a lot of the bases in DNA and RNA, formaldehyde will cross-link. You get one nitrogen bound to it, then you go through an imine, a double bond nitrogen, and then that's attacked by another nitrogen. So you get a carbon unit attaching two nitrogens. That's why that tissue, fixed tissue, cadaver tissue feels the way it does, because it's all cross-linked, almost like it was cooked. It gets very solid. So aldehydes, any aldehydes can do this. Aldehydes, very reactive. They're not good news. We don't want a lot of them. There are ideas that aldehydes are what cause hangover when you drink too much alcohol. Some people are very sensitive to that, and I'll come to that in a second as well. Acetaldehyde probably will cause some hangover, but it's metabolized into acetic acid in most of us at a certain rate, so it's not a problem. Methanol, however, is a huge problem. If you drink about 1 mole of methanol, like maybe half a mouthful, maybe 1 mouthful swallowed of methanol, you will get incredibly ill and probably die. It's because it gets metabolized into formaldehyde, and then you fix your tissues internally. The proteins in the lens of your eye are incredibly sensitive to this, crystallines. So the first thing is people will get cataracts if they get low levels of methanol, but usually they get such high levels. And once the damage is done, there's nothing you can do to reverse it. You've probably, you just don't have long to live. But if somebody's taken methanol in, you can use what we know about competitive chemistry at the active site, linked equilibria. So enzymes will respond exactly like competitive antagonists that I went through in the receptor pharmacology lecture. So we can add, if somebody's drank methanol, we can give them a lot of ethanol, and it will outcompete at alcohol dehydrogenase. The methanol will just partition into any of the water-containing body compartments, and you'll urinate out methanol. So you'll save somebody's life by giving intravenous ethanol. Also, where I'm from in Canada, they had some problems back in the day with small communities being very isolated, kids being very disenfranchised, abusing various solvents. They got their hands on things like photocopier fluid, which contained methanol, and they would drink this and get very ill. Some of them died. So the RCMP, Royal Canadian Mounted Police, that would police these areas, started to carry around vodka in the boots and the trunks of their car. And the idea was then you could give somebody this. It was an isolated community, so you wouldn't be able to get them intravenous alcohol. You might be able to save their life with ethanol if they ingested methanol. Problem was, these kids aren't stupid, so they knew that they could get an ethanol drunk just by running over to some police and saying, hey, I just drank a bunch of copier fluid. So that didn't work. It was well-intentioned, harm reduction, all of that. But you can still see every couple of years, there's newspaper articles about this, where they save people or pets by using ethanol. And it's through competitive binding at the active site. Ethylene glycol, this is antifreeze. It's very, very sweet. Diethylene glycol is the reason that FDA, well, actually, let's take one step back. Ethylene glycol gets metabolized by alcohol dehydrogenase to aldehydes. The aldehydes cross-link. Bad news. Diethylene glycol was put in an elixir of sulfonamide, one of the very first antibiotics. And this would have been in the 1930s, I think 1937, and over 100 people died. What they had was the antibiotic in a capsule or powder. They wanted a liquid form that people could drink. So they just took diethylene glycol, which is this molecule times 2, and it was 70–80% of that. And they added raspberry flavor and scent and all this. And all the FDA did at the time was say, these are the ingredients you say you have. We verify that these are the ingredients. A lot of people died because this got metabolized into aldehydes. It changed the FDA. The FDA then came in 1937 and passed new legislation and said, you have to show us that what you're putting in this drug and the excipients, the additions to this, are not toxic. And then I told you the thalidomide story where they had to do testing to show that it wasn't teratogenic. And then it wasn't until I think 1964 where they had to show that drugs were actually effective, that they did what they claimed to do. Through this whole COVID crisis, hydroxychloroquine and all these sort of emergency use authorizations, FDA people were really pissed off because there was no evidence showing that these were effective, but you get guys, they're very pushy, like Donald Trump saying, I think you guys have to authorize this, and they did. The data come out, they were wrong. Even if you're Donald Trump, if the data show you're wrong, you're wrong. Apologies, Donald. So with all of this, ethanol can be a treatment for this. Pets with ethylene glycol will very often drink this. I don't even know in this country if you guys have to put antifreeze in your coolant system, in your radiator, in your vehicles. In Canada, you certainly do because it goes down to -40. So we use a lot of ethylene glycol in the radiators. Sometimes they leak a little bit. This is very sweet. Our sweet receptor, our taste receptor, our G protein coupled receptor will recognize this. Dogs taste sweet, so dogs will lick up antifreeze, think it's great. Cats won't. Cats don't have a sweet receptor. So cats don't care for sweet things, dogs do. If the dog does that, you can then treat the dog with ethanol, intravenous ethanol. So said most people metabolize ethanol to the aldehyde and then to the acetic acid. Some of us do this quite slowly, and there's a mutation, a point mutation. The point mutation converts glutamate to lysine, and this particular mutation tends to be in people, if they trace their ancestry to Southeast Asia, Oriental blood seems to have this. Why they have it, nobody's entirely sure. It's also, this enzyme is useful for getting rid of various oxidation products. Some of those fatty acids I was telling you about in membranes and phospholipids, if they have double bonds and those double bonds get attacked by superoxide or hydroxyl radical, you will get something called nonenal, 4-hydroxynonenal, I think it is, or maybe it's 4-carboxynonenal. Anyway, it's an aldehyde, and these aldehyde dehydrogenases can metabolize that. They also metabolize nitroglycerin, glycerol trinitrate, into nitric oxide to relax blood vessels. So if you have this particular mutant, all of those reactions are going to be slower. This mutation is also being linked to esophageal cancer. We don't fully understand that. It gets back to evolutionarily, a lot of this stuff, think about it from an evolutionary point of view. Why would it be there? Why would people get mutations in it? Why would it stay in the population? It's just not random, it's being selected for. So initially, we're one of the few primates that can metabolize ethanol. And they think it was, we survived on rotting fruit for a while, over evolutionary time spans, where we were getting a lot of ethanol from fruit that had gone off, but we survived if we could metabolize it. If you can't metabolize it and get energy from it, it's of no use. Why certain populations within the world then got a mutation that doesn't allow them to metabolize the aldehyde, it's fascinating, absolutely fascinating. As I said, the aldehyde, one of the ideas is that is what gives everybody a hangover. If any of your friends have this, it's popularly known as Asian flushing syndrome. You will know they will not want to drink. Do not try to get your friends to drink. I made this mistake years ago before I knew better. It's like, oh, come on, we're all drinking, here, have some. And they would go completely red. They would vasodilate. They'd feel like crap because they get so much aldehyde dehydrogenase. So there's a lower incidence of alcoholism, much, 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 much lower in people that have this. Some people say you can titrate up your alcohol if you want to, and you'll upregulate Cytochrome P450, that 2E1 isoform. Not really good evidence on it. Nice idea, no evidence on it. Molecularly, though, let's go through what's happening here. So in the normal enzyme, LDH is aldehyde dehydrogenase. There's two forms of this. This happens to be ALD2H, which is a mitochondrial form, not the cytosolic form. And it has a sulfhydryl, a cysteine, an active cysteine at the active site, and it covalently links to this aldehyde, and then you get removal of this hydrogen with the 2 electrons of hydride onto NAD, you form NADH, and then water can hydrolyze this and you get the acetic acid coming off. In people with this mutation, this reaction is really slow, this water coming off. So you covalently link the enzyme and you acylate the enzyme, and then it's really slow coming off. So that's why acetaldehyde builds up and they feel like crap with just a little bit of alcohol. Disulfiram can do this to anybody. Disulfiram will wipe out this aldehyde dehydrogenase. It will covalently bind and not allow it to function. So disulfiram, it was discovered, again, accidental. Look at all past medicines. A lot of them were accidental discoveries. In a rubber plant where they were vulcanizing rubber, where you add sulfur and it can do something to the bonds so that rubber stays nice and springy and it doesn't deteriorate. The workers there on their Friday went home and they felt like crap because they were exposed to a compound called disulfiram from the vulcanization process. GPs at the time decided this might be a good way of treating alcoholism. You give somebody disulfiram, cross-links to the enzyme, doesn't release till you make, well, never releases. You have to make new enzyme. So somebody doesn't want to drink. What happens in actuality is people just don't take their drug. The drug's trade name is called Antabuse, and it hasn't worked all that well. The other thing I would say about this is some of the antibiotics that you guys, some of you who are medics will prescribe, the rest of us take them sometime. The knee-jerk reaction is always, do not drink on antibiotics. And I've looked back at the history of this. I've solicited student opinions, and some of them come with the idea that it used to be most antibiotics were prescribed for venereal diseases, so it wasn't a good idea to drink because you'll just spread the disease around more, lowers inhibitions, all these sorts of ideas. Can't come up with a really good idea on this or the truth of the matter, but looking around at it, there's only a handful of antibiotics that you really don't have to avoid alcohol on. And the reason is the ones that you don't want to mix with alcohol, there's whole lists of these. So there's a lot of them, but they fall into categories. Again, knowing the chemical structures and a conceptual framework for this allows you to just look at Wikipedia and look at the structure and know whether you or your patient could drink on this particular antibiotic or any drug compound. If the compound has a 5-member ring with 2 nitrogens up to 4 nitrogens, so imidazole to tetrazole, do not drink on those compounds. Those compounds inhibit aldehyde dehydrogenase, and it will work just like disulfiram, or if you have Asian flushing syndrome, a little bit of alcohol, you'll get really, really ill. You'll feel nauseated, you'll vomit, you'll vasodilate everywhere. So these are the ones to watch. The other ones, doesn't make a damn bit of difference. As far as I can tell, happy to be proven wrong, but I've looked all over the place, and most places say the guidance is it's just not a good idea to drink if you've got a bacterial infection without giving any mechanistic basis. It might be, but it might not be. I haven't seen the evidence. This is just a slide for you guys to look at in your own time. This is the stuff that I spend my time looking at over the year to year with these things. A lot of the stuff, the ideas I get are from this. I read a headline and think, is that real or is that bullshit? And that one about the hyperventilation with ethanol, I thought, not a chance. It turns out it was real. There's other ones. This poor girl down here died by drinking alcohol on an empty stomach. Go into that if you're interested and see. It apparently was real as well. They caused a metabolic acidosis. It's a very rare thing. A lot of us, unfortunately, at least I do, unfortunately, drink on an empty stomach at the end of the day sometimes. It can be deadly for some people. There's a lot of things about hand sanitizer now. A lot of hand sanitizer was made with methanol. Hopefully you guys would understand why that would be toxic, why it wouldn't be a good idea to drink it. Would it absorb through the skin? A lot of people are really worried about that. Might a little bit. I don't think it's a big worry, but all the guidelines say don't even use methanol as a hand sanitizer because it will contaminate you and the metabolic products are toxic. If we look at ADME, I don't think we're going to get enough absorption. I bet you could bath in methanol. Not going to try it, but just theoretically, I would think that. So you guys can look through here. Every year there's things about methanol poisoning being brought up, and some people intentionally drink it, unfortunately. There's this terrible story from India where it killed 80 people. They were doing home brew and they got the temperature wrong, and they basically distilled wood alcohol, which is methanol rather than ethanol. So some really tragic stuff out there. So in terms of Cytochrome P450s, these are these really incredibly powerful oxidizing enzymes that can oxidize anything other than, you got it, the halogens. Those ones are tough. They come in families, some like big, greasy, some like little and hydrophobic. Our friend CYP2E1 here is one for ethanol and paracetamol. They come in families. This is where you get a lot of drug-drug interactions. By inhibiting these, so that's one thing. Like I was talking about ethanol inhibiting aldehyde alcohol dehydrogenase. Here you can actually get inhibition of these. So if you normally think you're going to get this much drug and you take something that inhibits the same enzyme, you can get up to 7-fold, 10-fold more of that drug. You can take it from a therapeutic concentration to a toxic concentration. So this is really important. There's whole tables, there's whole databases about drug-drug interactions. It's hard to talk about generalities here. These ones you actually have to look them up. Really important to look them up. Most prescribing notes that come with drugs will tell you what you should and shouldn't take, and it often boils down to Cytochrome P450 interactions. So direct interactions at the active site, competition at the active site, that's one. There's another situation that can occur where you actually induce the enzyme. These are two different things. In past exams, I'm emphasizing this because I wasn't clear. That's evidence. It's my fault at that point. I wasn't clear in the way I lectured this, and people got really confused. So there's one where you get competition. Cytochrome P450, the normal amount we'd like to see, isn't there. So whatever drug you're giving is at a higher concentration because some other drug's blocking its normal metabolic pathway. The second way is by induction. This is from DNA to RNA to protein. There's cytochrome P450 inducers. These inducers act at the genetic level. They act through transcription factors, those nuclear receptors that I told you about, and they will transcribe genes for cytochrome P450, very often the one that's it's being induced. Just go back for a second. The cytochrome P450, that's the most, it's got the most targets. That's the one that's usually induced that causes problems with induction of cytochrome P450. Here's, I think, one of the best examples. It's a scary example if you're a woman of childbearing age and you want to control your sort of sexual health, and when you're pregnant and when you aren't, you can be on the birth control pill with our friend here, ethylene estradiol. There's that ethylene group, blocks interaction with cytochrome P450. But cytochrome P450 still metabolizes it, but it's slower. It fits in there, but it flips it. So it flips in the opposite orientation in the active site, and it oxidizes down on this ring here near this is a 3 position. So then we get a catechol. So it will oxidize it. It's just slower. So eventually you will oxidize it, but slower. If you take something like carbamazepine, this is an antipsychotic, a dopamine D2 antagonist. If you take a herbal remedy for depression, this stuff actually works. Clinical trials, it works. St. John's wort. These compounds will induce cytochrome P450, so they'll make more of it so that this reaction's a lot faster because you have a lot more enzyme. There are documented cases where women got pregnant after 1 dose of these things, so it can really increase it. There are anecdotal reports. This is basically GPs doing case studies about antibiotics causing the same effect. None of those have been verified beyond, case reports. So the jury's out on that one, but can cause what I put down here, surprise. This can be a problem. So these are how substantial these drug-drug interactions at the level of cytochrome P450 induction can be. This is what I was talking about earlier. Some people say you shouldn't take paracetamol and alcohol. They don't mix. Both of them are metabolized by the same enzyme. If you overdose on paracetamol and you slosh it down with vodka and there's enough vodka, you're probably saved yourself, because paracetamol will be excreted and the alcohol, the ethanol, will protect production of that toxic paracetamol metabolite. You can only get twofold increase in this. So alcoholics, they say, have this upregulation. It's only twofold. There isn't enough activity to cause this. There are certain people, all the government guidelines throughout the world say, be careful with alcohol, alcoholism, and paracetamol, dangerous, dangerous. When I first started teaching this stuff, I was going to have that in the slide here, why you shouldn't take paracetamol and alcohol. I researched it, looked at the evidence. It doesn't hold up. It's not true. Despite all the government guidelines everywhere, they're now saying, oh, well, it's for the precautionary principle, it might. The theoretical might, again, what Richard Feynman said, if your hypothesis doesn't fit the data, your hypothesis is wrong. This hypothesis, as far as I can tell, as far as experts in the area can tell, is wrong. It just doesn't fit. So you'll come across that with a lot of policies, even all the COVID policies right now. There are two sides to all of this. It's a balance. If it was all cut and dried, there would be no arguments other than the lunatic fringe on either side. A lot of this is nuanced stuff. You guys have the tools to go out there and read about some of these things and see if they work. I'll say a little bit more about some of the COVID stuff in my drug discovery lecture. So this is a grapefruit juice effect. In a nutshell, if you take grapefruit juice, it is enriched, or any citrus fruits, certain citrus fruits that have a lot of this compound here, bergamottin, it will inhibit cytochrome P450. This is that direct drug-drug interaction I was telling you about. Here, people are on a calcium channel blocker called felodipine. So that is a blood pressure lowering drug. This blocks the calcium channels in the smooth muscle of the vasculature. However, look at this. If you take 0, so this is felodipine in the plasma against time. If you don't take any grapefruit juice, the units here are glasses, versus 1 a day, 3 times 5 days. Look at the area under the curve here. This is just from taking grapefruit juice, which has this compound, and it can increase this. A lot of people died because of this, and some of the drug-drug interactions occur because of this, and you have to test for it. This is one of the reasons for some of the, what the FDA and the EMA require for, does your drug hit any of these targets? There's also something called a HERG, which has heart effects. Terfenadine, non-drowsy antihistamine, it affected this HERG channel. It's a potassium channel, and it will cause the heart to go into fibrillation. Ming Li will tell you a lot more about that in this cardiac lecture. So I said near the end, I would tell you a little bit about salicylic acid. I did. 1 year I had acetylsalicylic acid. It's metabolized, acetylsalicylic acid. Aspirin is metabolized into salicylic acid. So that's what floats around, other than your platelets, which get covalently modified by transferring that acetyl group. So here's salicylic acid. This is in your blood. So let's say you swallowed it, it distributed, it's in your blood. Your kidneys, think of your kidney as this. Physiologists will be horrified, but this is my idea as a pharmacologist of what the kidney looks like. We've got a filtering system here. It filters everything other than under 20,000 Daltons. Daltons are units of 1 hydrogen. So anything under than that will come through here. So small molecules will get filtered. In this filtrate, certain drugs will get pumped back into the urine, into the urine. Some drugs will just passively equilibrate across this. Some compounds, we don't want to lose glucose in our urine, so it's pumped back in. Some of the Greek terms for diabetes is sweet urine. So people would urinate and dogs would go and lick up the urine. Remember, dogs have a sweet receptor. If you're diabetic, you have so much glucose going out here that it saturates these reuptake transporters. They can't handle it, so you actually get glucose in your urine. When this happens, you can also get it increases the incidence of urinary tract infections. Other things that we might want: potassium, sodium, chloride, and where ions go, water goes. So this is how the kidney works. These drugs, we don't have carriers for them. So think about how they would partition across this. If you wanted to get more of it out in the urine, would you acidify or alkalinize the urine? And think about how you might be able to do that. It comes up on exams sometimes. So just think about it and then extend all this to any acid or any base. The very beginning of this lecture, my intro hook was on nicotine in vapes. And I said, if they could change that a little bit, they could probably get more nicotine out there. Some interesting side facts about nicotine. Back in the days before vaping was that popular, cigarette smoking versus pipe smoking versus cigar smoking. Cigarette smokers always inhale into their lungs to get the nicotine hit. The tobacco that goes into cigarettes is, I think it's kiln dried. There's air dried and kiln dried tobacco. And it makes it acidic, meaning this nicotine is going to protonate, particularly on this position out here, this nitrogen, because it's sp3 hybridized. The electrons are more likely, it's more basic, more likely to pick up a proton. So it's not going, that nicotine form, that species is not going to passively cross membranes if you smoke a cigarette. So you need to inhale it. Then you have the huge surface area of the lung. Even though a small percentage of it will be non-ionized, that's enough to get a big nicotine hit. You get huge hits when you inhale drugs, nicotine, cannabis, any of these types of drugs. That's why people like smoking crack cocaine. The surface area, you get a very fast, the circulation's fast, you get a lot going to the central nervous system then. So a pipe smoker, though, they'll hold the smoke in their mouth for quite some time. So it'll be buccal and sublingual. Pipe tobacco is air dried, I believe, which makes it alkaline. So if it's alkaline, neither of these nitrogens will have a proton and they won't be charged. So that nicotine can just cross through very readily. So just looking at this, if you were a vape manufacturer, I would think it would make a lot of sense to alkalinize your vape juice and you would get a lot more nicotine coming through. I don't know why they don't. Read that paper that I showed you. The pH on these things is all over the map. These people really need to take this course or think about medicinal chemistry, some of these effects. So what I want you guys to do is think about ADME, absorption, distribution. So that's going to be on some of these, just the protonation stuff. I missed M in here. We should think about M as well. It should be ADME, just not A, D, and E. Metabolism. How are we going to think about metabolism on this? It's got to be oxidized. But this nitrogen could already be a handle. We can do N-glycosylation. We could N-glycosylate that with glucuronic acid, and we could have a metabolite. We could do N-demethylation, just like on caffeine. We could oxidize one of these sp3 carbons out here with cytochrome P450. Then we'll have a hydroxyl. Once we have a hydroxyl, we can then conjugate it. Same thing with these positions out here. Probably not the one right next to the nitrogen. That might be a little sterically difficult, but maybe the ortho and para, or sorry, the meta and para positions. So think about this. Once they're oxidized, they're more polar, they will be released through the urine. So that's, sorry, I jumped ahead. That's what I want you to think about here. Don't jump to the next slide till you think more about this slide, please. Come up with your own ideas. And hopefully you got a lot of this. This is the real metabolism of nicotine. Some of these things, if you do health, private health insurance, and you say, oh, I'm not a smoker, they check your blood for some of these because the metabolites stick around for a lot longer than the normal compound. So you would know which compounds to test by looking at some of this. Hopefully all of these make sense. It can get really hairy, really complicated. These are the data, but we can do really good hypothesis guessing. to know how this probably would be metabolized. And we predicted, these are the ones that I think normally in class we'd go through this as an exercise, and usually we predict all of those. So thank you for your attention. I'll see you at the next lecture, and hopefully I have less audio-visual recording problems, get my damn camera on my computer working again. Take care. Bye-bye.